All right. Well, let's get started. As part of our Wolfram Technology Conference, one of the things that I think is really fun is that we have an awards ceremony for our Innovator Awards. So, welcome to this year's 2025 Wolfram Innovator Awards ceremony. And I had the chance earlier today, unfortunately only virtually, to meet up with all the folks who will be celebrating here today. I will thank everybody in our group of innovators for being able to be here at this time of day, which doesn't necessarily align with when the sun is up where they are. So thanks to folks who are in strange time zones. We appreciate you being here. Um, we started our Innovator Award program many years ago now to celebrate people who had done particularly innovative things with our technology. We build our technology, put a lot of effort into building our technology so that we can allow great things to happen in the world. And it's always really nice to see people do great things with our technology. And so every year we uh, pick a very small fraction of all possible people who've done great things with our technology to give Innovator Awards to. So, with we have, and I'll try and say a little bit about each person and the work that they do, and I will apologize in advance if I misrepresent or get wrong things that I'll say about these things. It's a very wide range of different kinds of topics that even for somebody like me who likes to know about lots of different kinds of things, it's a big stretch. Well, without further ado, let's go to the first person in our list for this evening. Our first Innovator Award winner is Aninda Sinha um, from the Indian Institute of Science in India and the University of Calgary in Canada. So Aninda is a particle physicist, mathematical physicist working on quantum field theory, and uh, most recently I think, has been using our technology for about a quarter of a century, but most recently has been working on formulas for pi, which you might not think would have anything to do with quantum field theory and those sorts of things, but Aninda has found a connection. So the story has to do with ways to represent scattering amplitudes, chances of particles interacting in quantum field theory. And long ago, in the beginning of the 1960s, a very popular approach was called S-matrix theory. And the idea was, let's not worry about what's happening inside all these particle interactions. Let's just define this matrix. This matrix was invented in the 1930s, but define this matrix that represents the overall effect of the interactions of these particles. And then there was a big effort to figure out, well, what forms could these matrices and the functions that corresponded to these matrices have that will be consistent with physical principles that we know about sort of things about how, as you change the energy, things shouldn't change, should change smoothly, and as you flip particles to antiparticles, things shouldn't change too much, and so on. In any case, that resulted in a collection of mathematical functions being identified that could represent sort of good S matrices. Well, one of those is the beta function, the Euler beta function, that is was invented back in the 1700s, but this was a use for that. In any case, the what Aninda did recently was to try to understand the sort of the correspondence between representing a an S matrix in terms of this beta function and the way in which one can think of that S matrix in terms of something like Feynman diagrams. Feynman diagrams are kind of space-time representations of interactions between particles. There's an analog of that in string theory that is sort of closer to S matrices. Boy, I'm getting a bit technical here, sorry. Um, but the idea is you've got this thing that sort of represents the whole answer about how scattering works, and you want to somehow represent that as decompose that in a sequence of pieces corresponding to particular uh, particular things that are kind of like string exchanges or particle exchanges or something like that. And the fact you've got this big thing and then you can decompose it into a sum of little things, that's kind of like a series for something like pi. And so the thing that Aninda has recently done is to find a new representation for series expansion for the beta function that can that can be thought of in this sort of physical way, but that also corresponds to a series for pi. And there's a parameter in what he's constructed that kind of goes from very traditional kind of Leibniz style series for pi to more Ramanujan style series for pi and so on. A lovely connection between kind of the mathematics of particle physics and the mathematics of things with quantities like pi. So our first Innovator Award of the evening goes to Aninda Sinha. I guess I have one physical award here, and good, we match. Um, thank you very much. The right. Moving on, our second award of the evening goes to Merck's Health, Economic and Decision Sciences HEDS team. The award is being accepted by the executive director of that team, Elamin Elbasha. What does that team do? They figure out the epidemiology and economics of particularly vaccines that Merck is developing or deploying. That's kind of a big deal in the world because many of those vaccines reach like 100 million people. So it's an important thing to do the underlying mathematical modeling for for those. And I think the um, apparently Elamin and his team have been involved in a whole series of vaccines, particularly HPV vaccine under the name of Gardasil from Merck. Um, and the goal is to figure out what the economics and the policies around vaccines should be by modeling the epidemiology of the diseases and the consequences of vaccinating different segments of the population. How do you make those kinds of models? Well, you use Wolfram language uh, if you're this team. And what are those models? Those models are versions of the SIR kinds of models that became fairly well known during COVID. Actually, fun fact, the those models sort of derived from what were called Kermack-McKendrick models that dated from the early part of the 20th century. The grandson of the Kermack and Kermack-McKendrick happened to be a good friend of mine in high school. So small world. But in any case, SIR models, the thing that gets tricky is that the population doesn't, people don't just sort of mix randomly. There are different kind of compartments of the population, and there are also different variants of diseases and things like this. And so the goal of modeling is to figure out what will actually happen in an epidemic. What level of vaccination do you have to give? Who are the important people to vaccinate to to deal with the spread of disease? How does this all work economically? Is it even worth developing a vaccine? If you do, how should it be deployed? And this team, I gather, has been responsible for briefing uh, lots of governments and um, on um, on on what vaccines to deploy and how to do that. So Our Innovator Award goes to the heads team at Merck and represented by Elamin Elbasha. Thank you.
Thank you.
Our next award of the evening goes to Gabriel. Oops, that is that picture. It goes to Gabriel Landi of the University of Rochester. And Gabriel is a professor of science and quantum science and technology. And in our world is uh, particularly notable for his development of the MELT package for uh, um, quantum um, quantum computations. Um, I I gather that Gabriel has been particularly interested in something that I also think is a very interesting question, which is how do quantum processes transition to classical behavior? In quantum mechanics, what's happening inside is all these separate threads of possibility of how a system can behave. But somehow there's a transition that's made to a definite outcome. One thinks of this as kind of the process of measurement and this question of how do you go from the all the quantum threads of possibility inside to the one we know what the answer is on the outside. And I gather Gabriel has been interested in kind of the interface between thermodynamics and the irreversibility that's typical in thermodynamic behavior and the kind of analogous irreversibility that happens when you go from all of these internal quantum processes that can kind of go back and forth, so to speak, to the definite, we got this particular answer in this quantum system. And Gabriel was telling me that he originally developed his MELT package. By the way, this question, what does MELT stand for? Is it something to do with solids melting? No, it isn't. It's the M is Mathematica, thank you, and the E is it's E to the LT, which is something where T is time, L, I guess, is the Lagrangian, and E is probably the exponential constant. And that's a piece of that's sort of the thing that you think about in the kind of time evolution of quantum systems. So he called his package MELT to represent that. Um, I think the um, uh, this um, uh, it's this whole study of kind of open quantum systems where there's little quantum mechanics happening inside, but then you're interacting with the whole outside environment. This is a very important area as quantum systems get applied in lots of different places. This is a critical part of kind of thinking about their application, whether one's doing quantum metrology for measuring magnetic fields very accurately, whether one's trying the stretch of making quantum computing work. In all these places, this whole question about the sort of transition from quantum to classical is is a critical one. And Gabriel has developed a lovely package initially for himself and now for the world at large, using Wolfram language to study these kinds of things. So our next award here goes to Gabriel Landi. Thank you. The- Our next award goes to Gareth Russell from the New Jersey Institute of Technology. Um, Gareth is an ecologist and has been using Wolfram language both in teaching and in research. He's uh, the associate chair and undergraduate director of biological sciences, and has been the been responsible for introducing Wolfram language to a lot of students at New Jersey Institute of Technology as part of their core biology courses, with labs being done using Wolfram language. Um, and I was asking, Gareth was saying a lot of the students he has are pre-med students who want to become doctors. And I was asking, why should doctors learn about evolutionary biology and ecology? And felt a bit silly after I asked that because in addition to understanding epidemiology and sort of the ecology of disease, Gareth reminded me that in areas like antibiotic resistance and in cancer, biological evolution is what's happening right there. When you when you have bacteria that are kind of growing on some plate and you put antibiotic down, and then more bacteria kind of develop that have been modified to to avoid the antibiotic. That's kind of biological evolution in action at a microscopic scale. And with tumors, the main issue is that after you give chemotherapy, that the tumor can evolve and the cells in it you can start to have cells produced that avoid the chemotherapy. And so being able to understand the sort of evolutionary biology of how that works is critical. I think um, one thing actually Gareth was telling me is the the strategies in chemotherapy, like pulsing the chemotherapy and so on, have sort of an interesting effect because the well, I guess in there's this sort of question of, well, why isn't it the case that everything just becomes resistant? And the strategies one can use to kind of maintain a population that is not resistant, that can kind of prevent it from being the case that the whole population becomes resistant. These are kind of stories of evolutionary biology now applied to very practical and important medical purposes. Um, Gareth also told me that his own research has been about animal movement. Um, I would say these are projects that, in some sense, have many legs. He's been studying, for example, a herd of goats in Africa, 16 goats, I think, um, where the goats have GPS collars on them and is able to watch, every second, where is every goat in the herd. Apparently, there isn't it's not the case that there is one king of the goats elected who is always the leader of the herd. There's a group, and it seems to change over from day to day. He also said he'd worked on elephants, where there is a sort of a fascinating phenomenon of kind of long-range coordination between elephants. How do they communicate over many miles? The answer is infrasound, and the dynamics of that starting to be understood. But Gareth has worked on the analysis of data and the modeling of these kinds of animal movement questions. So, pleased to present our next Innovator Award to Gareth Russell. Thank you very
Thank you.
much. Our next award goes to Harry Westfahl. Harry is the director of the Brazilian Synchrotron Light Laboratory um, in and this is a facility. It's the largest, I think, single scientific facility in Brazil, and it's one of the most advanced synchrotron light sources in the world. It's called Sirius, and Harry has been responsible for developing the experimental stations of this synchrotron light source. So you have, I think this is a 3 GeV synchrotron. So you've got a bunch of electrons going around in a ring, accelerated to 3 GeV, 3 times the rest mass of a proton, roughly. And one feature of electrons when they are accelerated in any way as they emit radiation, if you try to keep them in a ring, they're always going to be emitting radiation. They emit synchrotron radiation. And the idea that's a big nuisance if you're trying to sort of you have to pump energy into electrons to keep them to keep them going in a circular accelerator. But that negative thing for making an accelerator is a very positive thing for doing science, because synchrotron radiation, which comes in a whole range of potential frequencies and so on, it's a very intense source of electromagnetic radiation that can be used to analyze many kinds of things, whether it's doing X-ray tomography of crystallized proteins, whether it's studying materials, all sorts of different purposes. So Harry is the person who's figured out how to actually get those uh, those beams to come out with the right frequencies and so on by wiggling the electrons in just the right way with magnets. Apparently, in this particular system, it's been possible to the size of the packet of electrons that's circulating in the ring is just 1 micron in the orthogonal direction, which is a great achievement of kind of beam optics and so on. But what do you do when you get, for example, X-rays coming out? How do you actually direct them in the right place? Well, you have to have some system of mirrors made, I gather, particularly from very precise silicon surfaces that reflect X-rays at just particular angles and so on. The result of all this, lots of different experiments being done, taking days to weeks to do, and lots of data, terabytes of data being generated, and being handled with all of this. Uh, I gather that Harry has long been using Wolfram language to do computations, and since 2001 has been working on this particular facility and working out how to get all of those experimental stations to work using Wolfram language, and designing these systems and taking it all the way to blueprints and so on to actually have magnets produced. It's always great to hear these kind of sort of full spectrum uses of our technology, from the underlying physics to the kind of engineering deployment. So our award here goes to Harry Westfahl. Thank you.
Thank you.
Our next award of the evening goes to the WebAssign engineering team, represented here by uh, uh, Tony Parise, Josh Huber, and John Fowler. So if you have been studying calculus recently, or you have a kid who's been studying calculus recently, they've very probably been using technology built by this team and backed by Wolfram language and Wolfram engine. This is there's 1 million homework questions now in WebAssign set up using Wolfram language. And I gather at peak times when calculus and algebra and other quantitative subjects are being studied, there's 100 queries per second coming in real time, of questions being generated for students and students responding to those questions. The Why is this complicated? Well, it's difficult to make good questions at the right difficulty level, and to generate those to sort of generate them in real time. So if you're looking over somebody's shoulder, you're not getting the same questions they're getting. You're getting your own unique stream of questions. That's one part that's difficult. Another part that's difficult is figuring out, did the student actually give the right answer? You might say, well, is it the if it's a calculus problem, for example, they might write, 2 sine x cos x, or they might write sine 2x. Those are probably both considered right answers, but you have to be able to figure that out. And all the way back in 2007, 2008, the WebAssign team picked Wolfram language as the tool to use for those kinds of symbolic computations. And what they've done with it has been growing ever since. And at this point, also being able to give feedback to instructors um, about about the way that questions. I should say some of the questions were created by WebAssign and now Cengage. Some of the questions were created by instructors and then deployed through WebAssign. Um, and it's of course in as um, uh, we look forward to seeing what's possible as we all develop more kind of AI and LLM based technology around these kinds of things, and look forward to working with this team in those directions. But in any case, it's I'm sort of reminded uh, one of my kids who's now a mathematician, when she was younger, I think she was using this very system to do calculus homework, and I, as the very unendearing kind of parent comment, was saying things like, "I didn't think humans still did that kind of thing of doing um, doing calculus and so on, but they do, and some of the ones who do that uh, turn it into a whole profession and become mathematicians and things. But in any case, behind the scenes of all of those math questions that are being asked and answered of all of those students is the WebAssign team and the Wolfram engines that are powering in real time all of those mathematical questions and answers. So our next award goes to the WebAssign engineering team.
Thank you.
Thank you. Our next award goes to Mahn-Soo Choi, uh, who is a physics professor at Korea University. And we have a bit of a quantum theme going here because um, uh, Mahn-Soo is the director of the School of Quantum Computing at Korea University. And he has been studying um, uh, well, a variety of quantum systems and uh, representing, well, quantum information systems, quantum many-body systems, quantum spin systems, and to celebrate the fact that he's got 3 different kinds of quantum systems that he studies, he's developed a Wolfram language package named Q3, which is a symbolic quantum simulation framework, and that's also been represented in his recent book, a quantum computation workbook, um, that is based on his quantum simulation framework and work. And it was telling me about quantum phase transitions, something I have to say I have not uh, hadn't encountered as I should have done before. In a traditional phase transition, you are sort of heating up water and it's boiling. You're adding temperature, things are kind of getting more random as a result, and you are um, you have a discontinuous change. That's the notion of a phase transition from one phase of a material to another. Well, you can affect such phase transitions by things like external magnetic fields and so on. Um, but uh, what Mahn-Soo was telling me about was the idea of a phase transition at 0 temperature, where there's no jiggling around of things by thermal fluctuations. Instead, there are quantum fluctuations that jiggle things around. And the question then is, how do you have discontinuous changes of behavior as you change external parameters like magnetic fields in systems like this? And I got to go study this now because that sounds like a really interesting thing that I should know more about. And I'm kind of suspecting I will wind up with Mahn-Soo's Q3 system as my way to study that. So, uh, with that, our award goes to Mahn-Soo Choi, and thank you very much.
Thank you.
Our next award goes to Martin Ricker of the Institute of Biology at UNAM, the National University of Mexico. Um, Martin Ricker is a plant person who studies all sorts of things about computational botany and analytical biology in general. And the was telling me that he thinks he's now collected enough data that he could spend the rest of his life just analyzing it. But he's been out in the field collecting information about trees and other kinds of things. And now it's a question of how do you analyze all that stuff? And so for that, he's been using Wolfram language um, for a long time. And the to do both statistical analysis and modeling, um, and I gather started using Mathematica back in 1991. Um, and uh, the type of questions that it's been interested in is things like um, how do you analyze tree rings? What's the right way? What's the right sort of statistical methodology to use to figure out just how many tree rings, what the distribution of tree rings is, and so on? He was telling me that one of the issues is that for trees in the tropics, there aren't the same kinds of distinct tree rings that you get in outside of the tropics, because outside of the tropics, the trees grow when it's warm and they don't grow when it's cold, and you can see that recorded in kind of a succession of tree rings. In the tropics, they grow when it's wet and they don't when it's dry, and that's a much less, maybe in other cases too, and that's a much less regular kind of thing. So you have a much more complicated distribution of tree rings and a much more complicated story of determining the age and growth of trees. I guess another thing Martin was telling me that he's worked on is um, growth processes in and understanding the the kind of the the kind of things like exponential growth, but applied what the right growth curve is for trees and how you can deduce that from looking at different samples of trees and measuring diameters of trees and so on. Apparently, some of the new kinds of issues he's been involved in are things like can you uh, can you tell from a piece of timber what kind of tree it came from, and using different kinds of methods, including mass spectrometry and things, to do that. Also, I had interacted with Martin a decade or so ago because I've had a long time interest in various questions about biological growth, but one of them leads to the question of sort of what's the distribution of shapes of possible leaves in plants. And Martin has been involved in figuring out the diversity of plant species in Mexico. Apparently, there are about 30,000 species of plants in Mexico, about the same number in the US. And there's sort of this question of how can you identify these things? Can you do it from pictures of leaves? Can you do it from pictures of leaves that aren't on the plant anymore, but are collected in a museum or whatever? How do you do that? Martin was telling me he's been interested in using and has used our technology to do all those kinds of things. Um, so uh, and has also uh, helped not only with the kind of modeling and analysis, but also uh, um, with uh, the actual deployment of working with the National Forestry Commission in Mexico and so on. So our award goes to Martin Ricker. Still trying to figure out how to
Very
hold.
much.
Thank you. Our next award of the evening goes to Nathan Myhrvold. Now, I have to say, I always know different people who've been using our technology a long time and who we give innovator awards to to a different extent. I've known Nathan for a very long time. I was trying to figure out when we had first met. Nathan got his PhD in physics at Princeton in the early 1980s, and I think we might have met sort of just in doing physics because uh, Nathan's thesis advisor was a friend of mine, among other things. But one very distinct memory that I have, which must have been around 1983, was Nathan and a couple of friends of his coming to see me one evening at the Institute for Advanced Study and saying, "We've started a software company. I think it was called Dynamical Systems."
It
Um,
was.
okay, good. Memory still works. We started a software company and we've developed a Windows system. And I'm like, how can this work? Microsoft has said it's going to develop a Windows system. It hasn't delivered it yet, but it said it's going to develop it. How are you going to compete with Microsoft? I said, and maybe you should just sell your company to Microsoft. Well, I think a few years went by, but eventually that's what happened. Nathan sold his company to Microsoft, and Nathan himself went to work at Microsoft, and over the course of not very many years, ascended to the position of Chief Technology Officer at Microsoft, along the way starting Microsoft Research. And Nathan, some people like myself like to, in some ways, keep their lives simple. Nathan, I think, does the exact opposite. Nathan has been involved in so many different kinds of things. After, I think, 14 years or so at Microsoft, then started intellectual ventures for, among other things, collecting inventions and inventing things. And as well, Nathan, like me, gets to do kind of science as a hobby and at Intellectual Ventures has assembled a very, I would say, Edison-like collection of capabilities in a lab. I think the time I visited there was a chick hatchery and there were lasers and there were just all kinds of crazy pieces of equipment for investigating and inventing all kinds of different things. Along the way, Nathan has been a huge user of Wolfram language and Mathematica. Um, Usually, um, he is to me, he's a reporter of bugs, in very obscure corners. And you always know that somebody is a very serious user when it's like, how can I get more cores and run more things in parallel and so on. Um, Very recently, uh, Nathan sent me an email that said, actually, this isn't a bug report for once. This is a case where um, the where things that one might not have thought would work just worked in using the interior point method for find minimum. Why was Nathan doing that? Well, I said Nathan does a lot of different kinds of things, and I have to tell a few micro Nathan stories. I mean, I think uh, uh, the there aren't that many people in the world, maybe only just one, who have a T-Rex skeleton, Tyrannosaurus Rex skeleton in their living rooms. But Nathan has such a thing, along with a lot of other kinds of objects. Um, the I think Nathan at some point foraged the on-off switch from John von Neumann's computer. I think that was
Yes.
maybe a bonus for being a trustee at the Institute for Advanced Study or something. Um, but also contributed to the reconstruction of the Antikythera device, uh, got a Babbage difference engine, funded part of that, and got one for himself. Um, and uh, uh, I would say that the uses that I know that Nathan has put Wolfram language to, um, I know at Nathan's house there's a funky staircase, which uh, I hope people don't trip on it or anything like that, but I gather was designed as some kind of 3D curve, um,
Yep.
and um, that's that's one, and then of course um, there's all the studies of asteroids and the reflectivity of asteroids and so on. And then there's the study of the recent study of snowflakes. It had always been the case that a chap called Bentley was sort of the definitive snowflake photographer. Nathan has become the definitive snowflake photographer of the 21st century. I will say that somehow, in addition, I think, to making great visualizations with our technology, Nathan is also a very serious photographer of lots of kinds of things, whether it's wildlife or food. And this is another thing when I in past years, Nathan would say to me, "Well, I'm doing all this stuff at Microsoft, and I'm also volunteering as a at some restaurant." And it's like that's a very weird thing to be doing. Turns out this has been a lifelong interest of Nathan's that became extremely serious, and uh, um, the is developed this whole modernist cuisine uh, 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 collection of books and so on. I thought I had written big books, but Nathan has written books that are much bigger and much heavier than anything I have written. And some of those books are about general cooking, again, using Wolfram language a whole lot to study things like the temperature profile of a piece of meat that's being cooked or whatever else. But then uh, Nathan had sent me his latest book that turned out to be about the subject of bread, and an absolutely giant. I think there's a small version. I think I got the small version. That the full version is still much vaster. How could you write so much about bread? Well, there's a lot to say about it. Nathan was just telling me today that uh, there's always the question of how do you when you bake bread, well, there's sort of heat and there's transmission of heat, and you would think that's you're just solving the heat equation, but it isn't as simple as that because the bread expands as you heat it. But apparently, also, Nathan and team discovered an effect for the transfer of heat where little bubbles get produced that pop and kind of squirt heat into the interior of the bread. So, no doubt, this is something that bakers have experienced forever. But thanks to Nathan and thanks to hopefully lots of differential equation solving in Wolfram language, more is understood about that. Um, I have to say that um, the Nathan has um, uh, published papers and done work in just a huge variety of different areas. But he was telling me he now is adding yet another area, which is statistics, and has just developed with Wolfram language a new methodology for understanding the question of whether not just is what's the probability that this data point lies within a certain region, but what's the probability that this whole curve lies within a certain region? I gather that's the latest application that Nathan's made of our technology. I mean, there've been so many. I've totally lost track. I mean, I remember there was also things like analyzing networks of patent citations and so on. It's this is what we built this technology for, is to be able to do all these very different kinds of things. And Nathan has uh, been a wonderful example of the lots and lots of different ways that you can use our technology. So our award goes to Nathan Myhrvold.
Okay, thank you. I'm honored.
Thanks. The Our next award goes to Qing-Hong Cao. Oops, that's Qing-Hong Cao of Peking University.
Hi.
Hello. And uh, Qing-Hong has um, been using Wolfram language and Mathematica in his courses, and most recently has written a textbook about quantum mechanics that is considered a core textbook now in China. That apparently was the result of about a decade of teaching with Wolfram language, and it's he's been able to use Wolfram language um, as uh, uh, as the generator of pictures and exercises and so on in his book. His research is about particle physics, and I see on the page there a Feynman diagram. Um, I gather he's been interested in um, uh, approaches to computing things about, for example, top quark production, and I in long ago. Okay, uh, one of my efforts that got me into doing symbolic computation was calculating particle physics processes. One of the ones I computed back in 1977 was the production of what were then charm particles in proton-proton collisions. Well, in later years, the B quark and the top quark got discovered. And so now one's interested in computing the production of things like top quarks in things like proton-proton collisions. And uh, back when I figured these things out, it was like two gluons come in and a quark, anti-quark come out. But there are more exotic processes that are possible. And Qing-Hong has studied processes where just one top quark comes out instead of a pair, just one comes out, presumably through W boson interactions. And I don't know if that's been observed yet, but that's seems like a really interesting thing to look at. So uh, our next award goes to uh, uh, Qing-Hong Cao. Thank you. The Our next award goes to another person I've known for a long time, Sheldon Axler. Uh, Sheldon is now an emeritus professor at San Francisco State University. Um, he said that now that he's retired, he's doing more math and writing more books than ever. Um, that's I that's always a great thing to hear. Sheldon was telling me that he uh, first started using Mathematica, now Wolfram language, um, back very soon after 1988, when Mathematica was released. And he had a particular problem he was trying to study, which was you have a sphere, and you're thinking about it, solving the Laplace's equation or Poisson's equation for um, for the potential inside the sphere, and it's a problem where you've specified what the potential is on the surface of the sphere, and you've specified that that set of potentials in terms of polynomials. And the surprising fact is that polynomials sort of go in to specify the boundary conditions, and the potential on the inside is also represented by polynomials. And Sheldon was interested in studying that, and that took lots of algebra, and that's what he first started using Mathematica for, and using its pattern matching capabilities and its algebraic capabilities to untangle that problem. He was telling me that he's still interested in that problem today, and was recently got a variant of that problem where instead of specifying the value of the potential, you're specifying derivatives of the potential on the surface Neumann problem instead of Dirichlet problem, something which apparently came up in practice for folks at UCSF studying um, studying things for MRI and trying to reduce electromagnetic interference with MRI. But one of the things that so Sheldon has uh, created lots and lots of things with Wolfram language, particularly harmonic function theory package that for solving this problem of harmonic functions, functions that satisfy the Laplace equation and so on. What Sheldon is most famous for to many people is the books he's written, the textbooks he's written. He's written many textbooks that have had a lot of influence and been very successful. I know at least two of my kids have used his books. In fact, I think more than one of his books. And sometimes I know in at least one case it was like, I don't understand how this works. Why don't you look at Sheldon's book? Oh, now I understand it after reading how Sheldon described this. The He's written one of his books is about linear algebra done right, and that book just went into its fourth edition. And I think in addition to the technical aspects of the book and all of the pictures being generated with Wolfram language and the exercises being created that way and so on, um, there's sort of a practical aspect of that book. The fourth edition, Sheldon convinced the publisher to let it be distributed as an open source textbook. And apparently this has worked as planned because it's become very popular with translations into all sorts of languages happening. But it's also the additional popularity of the open source downloadable book um, has has led to more rather than less purchases of the actual physical hardcover book. So probably a good model for many kinds of things, um, but um, a nice thing to see that more people in more places are getting the benefit of Sheldon's expository work. So our next award here goes to Sheldon Axler.
Thank you.
Thank you. Our next award of the evening goes to Thomas Hahn of the Max Planck Institute for Physics. Thomas Hahn has been for a quarter of a century the keeper, developer, and developer of fine arts. Fine arts is a system for generating diagrams, Feynman diagrams for particle physics. And Thomas Hahn himself has been not only a developer, but also a physicist user of fine arts, generating and visualizing Feynman diagrams and Feynman amplitudes and so on, and has developed a variety of related tools for Feynman diagram computation, and has one might have thought that every Feynman diagram that could be evaluated has been evaluated, but it isn't true. And there's always more to do, both in the standard model of physics and in generalizations of the standard model, fine arts has been there as a core tool for doing Feynman diagram computation in physics. Both in QCD, Thomas Hahn was saying that's the simpler case. I have to say, I did a lot of calculations in QCD. It was always seemed quite complicated to me, but I was doing those things before fine arts existed. But electroweak interactions have sort of more diversity of different kinds of things that happen, and that's a perhaps some even stronger use case for fine arts. Fine arts, as I say, has been an important tool in the physics community, built in Wolfram language, and for a quarter of a century developed by Thomas Hahn. So our next award goes to Thomas Hahn. Thank you very much. Our next and final award of the evening goes to Thomas Landsberger of Enoda. And Thomas has been using Wolfram language for a long time. What he's been doing at Enoda is developing kind of a new generation of power control systems, building a kind of a transformer for power that can help maintain the electrical grid in a stable way. And I guess he was telling me one of the difficulties these days is it used to be the case that power was produced in power stations, but now lots of people have solar cells, and now lots of people are generating their own power and sticking it on the power grid at random times when the sun happens to be shining or when they connect themselves to the power grid. And not only that, at a power station, when you're doing power generation by having sort of rotating machinery and so on, you end up with three-phase power. But when you're just sending in power from photovoltaics, it tends to come in as one-phase power. And there's the challenge of kind of stabilizing the power grid given all of those characteristics. What Thomas has worked on is the creation of a new system that has 12 coils arranged in some kind of spherical configuration, and with active control done with semiconductor switches to keep. There's a picture of his device to stabilize things for the power grid, and the computations for this have been done with Wolfram language, and apparently generating often huge algebraic expressions and so on, representing features of these systems, and constructing the control system that is needed to keep this system operating and maintaining the power grid. Apparently now a couple of Enoda systems have been deployed inside substations. I was asking, how will I be able to know if an electric power substation has an Enoda device inside it? And Thomas said, one of the ways you'll know is on top of the little building that houses the substation, there'll be an antenna, because the plan is to have all of these devices networked, and that antenna is connecting them to the network, so that you can have, if you have 1 million of these devices deployed in different substations and so on, they can communicate with each other and make use of Thomas's technology to help maintain the power grid. I'm somehow reminded of this story. Maybe it's even an apocryphal story about something that's often quoted in kind of the development of control theory, of when Edison first had his electric generating station in New York City, that there were two generators, and one of them was running too fast and one was running too slow, and somehow by putting some band between them, it was possible to stabilize them. And that's sometimes quoted as an early story of control theory. Now Thomas and team has a vastly more sophisticated version, but maintaining the stability of the power grid. So our last Innovator Award of the evening goes to Thomas Landsberger.
Thank you, Steve. I'm honored.
Thank you. All right. Well, it's been great to celebrate these innovators, and it's just lovely to hear about and see all these uses of our technology. We're building a pure tool, so to speak, and to get to see it used in all these different ways is very satisfying. And to hear about people who have for decades been using the technology we've made is just wonderful. And it's a very satisfying thing to see that the things one puts so much effort into get such wonderful use. Well, I think that concludes our Innovator Award ceremony. And for folks who are watching this in the outside world, that concludes our program for today. For folks who are part of our technology conference, we're going to go on with the Q&A that I didn't have a chance to do at the end of the keynote from yesterday. So thank you all for joining us, and let's now transition